Okay, so this is our last neural network related lecture. And this is mainly just tying up some things about these kind of, third generation neural networks is what I call them, neuromorphic engineering and so on. And so where we stopped is talking about kind of whereas the majority of neural networks that we hear about are your standard artificial neural networks, which really are just fancy generalized linear models kind of chained together in, programmed in a very conventional way, just combinations of functions that act on linear combinations of things that have turned into sort of tensor processing networks and so on and so forth. And so kind of the next step in this is, neuromorphic engineering. And spiking neural networks, specifically. Or SNNs. And spiking neural networks are focused on this idea that we have abstracted maybe too far away from the actual neuron, and maybe there is a bunch that we've left on the table that could still be gained by actually mimicking the actual spatiotemporal function of what's going on in real neural networks. And so if we recall, in our simple, version of a real neuron, you've got, the cell body, dendrites, you've got your sort of dendrites out here, your axon here, and traveling down the axon, whenever there's enough of a synaptic potential accumulated over in the dendrites near the cell body of the neuron, it once it crosses a threshold, the neuron depolarizes and has this spike potential. And so you get this action potential that looks a little like this. So if this is 0, then you get this spike that goes well above 0, comes back down for a little bit, and it travels down the axon, as we've talked about before. And so if we were to zoom in on this spike, it would look something so if this was time, and this was potential. So, like I said, all cells in your body have a negative charge. Immediately outside the cells, there's a positive charge. That's why you're not charged. You're neutral charge, but every cell is slightly negative, and the outside environment is slightly positive. So, with these neurons, they start at that slightly negative, but then once they get enough synaptic potential accumulated, then you get, so you get some synaptic potential start accumulating, they rise, they hit some threshold. Let's say the threshold's around here or so. And if they hit that threshold, then they will continue to rise even after the synaptic potentials have been removed. And they reinforce that until eventually that reinforcement stops, and then they kind of collapse. They go down beneath where they started, come back up, and eventually come back and settle. And so this is a so-called action potential. And this behavior over time that is represented behind me here has been modeled in all sorts of different ways. So you can look up, if you were to look up an action potential, you can find a bunch of mathematical models. And so there's ordinary differential equation models of how neurons work, and specifically action potentials. And so you get things like the Hodgkin Huxley models. There's integrate and fire models, and so on. And so these are mathematical models of how people think that neurons work. So what the spiking neural network folks did is they said, well, there's subtle differences in how these neurons kind of connect together. We computationally could initially in high performance computers, and so some of the early frameworks were things like, there's a SNN frameworks here. So some of the early frameworks like SpiNNaker, this is basically a supercomputer, or HPC, that simulates networks of analog models of spiking neurons. So this is sort of first generation of spiking neural networks. We're not actually spiking elements, but they were these sophisticated computers meant to allow you to connect lots and lots of analog models, so computational models, differential equation models that could be integrated inside a computer to generate these. And you can network these things together so that as some of these fired off, then they would generate signals that would generate synaptic potentials at other ones, and so on and so forth. And you could start experimenting with building your own artificial spiking neural networks. And so, but as time went on, then you got actual hardware platforms from companies that you've probably heard of, like IBM. So you had things like IBM TrueNorth and Intel Loihi. And so these are true hardware platforms. So you can picture, chips. So finally, you've got spiking neural network chips that you can actually, and you can find plenty of papers where you can buy an Intel Loihi now, today, and put it on a quad rotor and have it process inputs from the outside world, and then process them using spiking neural networks and have them produce outputs and have it drive the quad rotor. And but internally, it's the same basic idea, is that in these elements here, you have grids of, we'll say, grids of components that may, in the case of the hardware ones, mix analog electronics with digital electronics so that you have the ability to choose what action potential model you want, and character and parameters of those action potential models and how they're connected together. And so that's the way that you can actually build these neural networks. So this is actually, you're really building networks of neurons. I mentioned that in an artificial neural network, like what you do with conventional neural networks, if you were to download a PyTorch or these, or TensorFlow, these frameworks that are made to do standard machine learning tasks, we call those neural networks, but they're not implemented as actual neurons wired together. They're just a data structure that stores, a vector or a bunch of vectors packed together of data that then get operated on by mathematical functions, generating new vectors that get packed together and get operated on. It's just a little bit of math. And here you actually have networks of neuron-like elements wired together. So now we're actually getting really kind of close to that. And so those are some of the platforms here. Some of the interesting advantages of these is that a lot of these frameworks, the hardware frameworks, promise to be very low power. So if you, so right now, like, the military, for example, is always interested in this acronym SWAP, size, weight, and power. And so they're interested in, so if I say swap, so that's size, weight, and power. How do we pack a whole bunch of computing in a small space with a small battery and have it do amazing things and last for very long amounts of time? And so SNNs are pitched as one way to solve this, is how to bring a lot of the neural network approaches that we've seen have so much success on high performance computing, scale them down so that they actually can be implemented on a very small platform that can still do many of the same things. And so this, why do we have these spiking neural networks? It's sort of two-pronged. It's one, because people think that the abstractions we have in artificial neural networks might be losing something. So there might be something special about actually implementing true spikes as opposed to just these values that have continuous values. Remember, in action potential, it always goes up to the exact same height. There's no difference in height. It's not like some action potentials are higher and some are lower. They're always the same height. The difference in action potential is in density. So you can get action potential, so you have high density. And so over time, you might get, lots of action potentials. Then you have low density. Where all your action potentials are the same height, but you get major spaces between them. So in nature, we have value encoded in time. So this is a temporal coding. And so the thought is maybe all of the abstractions we've done to keep the convenient kind of spatial coding we're losing something. And if we go to the sort of temporal coding, we can start playing with all of these analog parameters, and there's a bunch of cool computing we'll get out of this. So that's one half of it. The other half of it is that maybe we can actually build things that use far less power. Now, why would these use less power? Well, the actual computing, when things are off, then it's kind of like the cells of your body. They just sit there and at rest. And it's kind of the same idea here. You only need energy to temporarily reconfigure the neuron to have it fire this action potential. And then after you've expended that energy, it goes back to a quiescent state. It goes back to rest. And this idea that these things sit at rest this amount of time, and they may not need power or that much power to keep them at rest, suggests that maybe computing architectures that use spiking networks are going to be far more energy efficient than those that use more traditional artificial neural networks, which are built on top of good old-fashioned computers like that. So that's kind of the motivation behind that. And there are other really interesting frameworks that people are proposing that are kind of coming out of the laboratory now. And I wanted to at least expose one of those, and then I'll take some questions here. But another angle that people are, so I just want to emphasize that these, like TrueNorth and Loihi, if you look at each individual artificial spiking neuron, each artificial spiking neuron on these two platforms, they're pretty complicated. They've got a lot of flexibility. They've got a lot of different components. They can be configured in different ways. And they allow you, again, to implement lots of different patterns. So implementing sort of different ODE models of how these neurons work inside each one of these artificial neurons here. Now, there are a few others who've been saying, what other electronic components are already kind of neuron-like? And maybe they don't give us as much flexibility in tuning the properties of the neuron, but they really might allow us to build high-density networks of spiking neural networks that will get us most of the way there. And one example of that comes from neuromemristive approaches. So, write that here, neuromemristive, I should say, approaches. So just to give a quick background here. If we think about a standard resistor in electronics, a resistor is something that behaves by Ohm's law, which means that the voltage and current are linearly proportional, or in other words, V equals IR, where this here is the slope of IV curve. In other words, if I were to draw, let's say I draw current, or I on this axis, and I draw voltage here, or V, and I'm talking about, a little element, looks like this. This is our little resistor element, and I've got a certain amount of current I going through it, and I can measure the voltage across it here. And so the idea behind a simple resistor is the more current you move through it, the more voltage you get out, and they're linearly related. And so I can get something that looks like that, where this slope is the resistance. So if I increase the current a little bit, I increase the voltage that I see across it. Simple resistor. So standard, most people take in some sort of entry-level engineering course. You probably had to maybe learn about circuits or resistor or whatever, say anything like that. So that's kind of a normal resistor. Now I'm going to introduce a different component you probably don't talk about a lot, at least in entry-level electronics courses, and that's a memristor. So the thing is, there are elements that can be built in the laboratory. They're not as easy to find naturally, but with some fancy semiconductor approaches, you can build something that combines the electrical properties of a resistor with the sort of magnetic properties of, we'll say, an inductor. I don't like to say that, but it's a ferroelectric component. So there is this sort of, I'll call it a ferroelectric memristor, which is short for memory resistor. And in a memristor, if I draw my IV curve again, I get current here, voltage here. And so in a memristor, at small currents, it looks like a resistor. So I'm about to draw an IV curve here where at small currents, as I increase the current, it's going to start increasing the voltage across it at a particular level. Okay, so it would look something like this at small currents. Now, when I hit some critical current, something interesting happens. I end up getting what's known, I think, is a pinching of the IV curve. At some higher current, what the IV curve actually tilts down and it forms this funny bow tie. So what I'm saying is that, let me see if I draw arrows here. I start out at some current and I get higher and higher. And at some point I get to some high current and then the voltage drops. And the voltage follows this other curve until I get to a sufficiently negative current, and then it follows the other curve again. So it follows this figure-8 shape, characteristic of a phenomenon I'll call hysteresis, which I'll show, it'll be a little clearer when I actually draw a resistance plot here, or history dependence. So what I'm saying here is that the relationship between current and voltage depends upon the history of the element. This is a passive element. So it's not like an element that you have to keep the power on to do this. This is an element that internally, it changes its, this is an oversimplification, but it changes its magnetic properties. It reorganizes its magnetic domains when you push it hard enough. So you drive enough current through it, and it sloshes its magnetic domains into a different area, which changes the IV characteristics, which changes the resistance. So effectively, it gives me, so if I'll choose maybe a different color, it's like down here, it's at one resistance, and up here, it's at another resistance. So you can think of this as slope as R2, and this is slope as R1. It's like it has two selectable resistances. And that's what makes it a memory resistor. This is a memory element. There are resistive RAMs, so resistive memory frameworks that are based off of this idea. And it can be extremely low power because it remembers what resistance it was last, even after you turn the power off. So you can say you're a low resistor, and then you can turn the power off, come back later and say, actually, you're a high resistor. And as long as you query it with a low amount of current, you can tell what resistance it is without changing the resistance. But if you drive a little bit more current, you can change the resistance. So it has the ability to both switch resistances and be querying resistances. And so this is effectively a resistive memory element. So a lot of times when people draw these, instead of drawing these IV curves, they just draw resistance curves. And so you could imagine drawing, for my memristor, I could have a curve that looks, I think, something like this, where I've got my current I, and I effectively have two resistances. I have a resistance up here and a resistance down here. So we can call this one, just to be consistent, my high resistance was R2. So I'll call this one R2 and this one R1. And the idea here is that if it's at high resistance, if I drive it with enough current, it will drop to low resistance. And so I get this curve that kind of looks like this. And this here is a hysteresis loop, which is common characteristic of systems with memory. And so this is saying here, at high current, resistance drops. And at low current, resistance increases. And the key here is that at intermediate current, which includes 0, resistance is maintained. And that makes for a low power memory element. It's effectively non-volatile. Meaning that if you turn off the power, it will maintain whatever its resistance. So you could call resistance 2 might be like a 1, and resistance 1 might be like a 0, and you've got a binary memory element. Okay, what does this have to do with neural networks? We're about to get to that. Are there any questions on this basic idea of the memristor? It's a special type of element. Most people learn about capacitors, inductors, and resistors, and kind of basic, intro to engineering sort of stuff. And this is kind of a more exotic element that was hypothesized to exist for a long time. And recently, they actually figured out, relatively recently, how to build one in at pretty, low scale, at small scale, in sort of high numbers, so that it could become really a part of the toolkit that computer engineers could use to build fancy memory technologies going into the future. So questions about that? Okay. So the reason I bring this up is that there is this paper, which you can find on Canvas, where a couple of folks thought about a clever way to implement these memristors to create a neuromorphic framework, extremely simple neuromorphic framework that could do a lot without a whole lot of fancy training or anything else. And so this is a paper that is by Boyn et al. I think it's 2017. And it's in Nature Communications. By the way, the Nature Communications, it sounds like that should be a journal about like communications theory or signal processing or whatever, and it's not. It's just that the people at Nature figured out the great way to make money would be to bring out other journals that were easier to get your papers into than Nature, but people would still want to get their journals into them or their articles into them because they carry the same cachet as Nature. So it's so Nature Communications, the communications are the papers, and so it's not papers about comm. And it's a little confusing because there are like other things where it's Nature, the thing that all the papers are about. But yeah, that's largely a marketing decision to take science and nature and then diversify them into journals that allowed them to accept more papers without carrying the same cachet as their flagship journals, without actually having the same sort of processes and things like that. So that's why it's communication, but it's not really a communications paper. It's just a paper. That's why it's in communications. Anyways, I digress. So what Boyn et al. Did is they realized that they could implement memristors in a crossbar architecture. And so if you've ever, how many people are familiar with an FPGA? Does this sound familiar to anybody? Sounds okay. So you know that there are these gate arrays. If you remember, back in, if you at a computer engineering course, you might have taken some time, might have learned that there's ways you can implement logic using arrays instead of using gates themselves. And so you can create these. So I'm going to draw. I don't know how sort of 3D I want this to look, but I think it's fine if I just do it this way. I'm going to make these lines a little straighter. So imagine I've got a bunch of these lines. You can just think of them as wires, all going vertically here. And intersecting with them, I'm going to have a bunch of these horizontal lines going through here. And I'm going to consider these to be inputs maybe I'm going to draw that beneath it, but it's the same idea. I'm going to say these lines here are inputs, and these lines here are outputs. And I can say, think a gate array like FPGA. And this is what I'm gonna be calling a crossbar architecture. And so what goes on here? Well, if you were to imagine that you put on the inputs here, like you could put like, a bunch of digital inputs that are encoded as voltages. And, if you put them on top of here, and you treated these as outputs, then you could choose which wires to connect together and which wires to leave open. And by doing so, you could actually implement logical operations. So if you wanted a certain output to only be on if there were certain combinations of inputs, rather than creating gates to do that, there are ways in which you can fuse these different junctions together that will end up combining inputs together so that you can have multiple inputs kind of tied to a single output, and you can end up creating kind of logic out of those fusions. And I don't want to get into too much details about the gate array stuff, because I think it'll become more clear in how this memristor stuff is here. So what these folks did in this Boyn et al. Paper is they put memristors at every junction. So I'm going to just put a little memristor here, here, here. So basically, we have memristors at every junction. And those memristors connect input to output. And so what does that do? Well, what they found is if they could build this crossbar architecture with memristors at every junction here, then what you could do is you could put patterns on the input. So spiking patterns on the input. So as an example, if I've got an image, these could be, for example, pixels of an image. And you can think, if you're familiar with the data set, MNIST or fashion MNIST, etc. So little bitmaps, like we talked about for unsupervised learning. And so some of these pixels will be, let's think of just black and white to keep things simple. Some of these pixels will be black and the other ones will be white, and so on. And let's say the black ones are encoded with spikes. So, high spikes, that voltage spikes, they just go up to, they have a quick spike. So, so let's say, yes, we're saying that black corresponds to a spike and white is no spike. I'll say spike, and it's, let's say, in voltage or current. All right, so what ends up happening here is that these spikes, when there's a large enough spike from multiple inputs, you can actually end up triggering the memristor to flip to its low resistance state. So all the memristors start high resistance, and then if there are these large spikes, or you could say no spike, I could say or negative spike. That could be another option here. So so if you get a bunch, so in this case here, like I'm looking at this one, and this one. So these three happen to all spike at the same time. And so this one spikes and it actually lowers, maybe it because this is at some resistance, a little bit of the current comes down through, and it hits all of these memristors as it goes down through here. Now, this one also generates a little bit of current coming down through this output here, and this one generates a little bit of current coming down through this output here. So gradually what's happening here is that these memristors are actually seeing more and more current. So if there's current coming in, then the places they combine, if there is an output line where they can all combine, then the memristors in this output line feel more and more current, and it's more likely that their voltages are going to drop. And as their voltages drop, it might draw more current out of the rest of them here. So what ends up happening is over time, you can get a spontaneous reinforcement of particular memristors for particular patterns. So this pattern might reinforce over time resistance in these three will drop. And what is going to happen with that is that if that happens, and in the future you get these three pixels turning on, it will be very likely that this output will produce a lot of current relative to the rest of these outputs. So you can actually look for spikes on the output. So I'll put maybe a different color, spikes on output. So I'm glossing over a lot of the kind of little details here, but the basic idea is that you just set this array up. You don't put it in training mode. You don't have to power it necessarily, but you just start peppering the input side of it with spikes that correspond to different patterns. And if certain patterns, so let's say every time you see an A, then these pixels light up together. And every time you see a C, maybe this pixel, and this pixel lights up together. When every time you see a Z, maybe there's a different set of pixels that light up together. Well, what happens over time is that you end up getting a segregation on these outputs of these different patterns, or at least you get a coding that can occur here where you can actually start noticing that every time you see an A, you see a particular distinct pattern on the output of spikes. Whenever you see a B, you get another distinct pattern of output spikes. Every time you see a C, another distinct pattern of output spikes, and so on and so forth. Early, when you initially show the patterns on the inputs, you get random stuff on the outputs here. There's no way, you can't be discriminated. But by exposing the same input over and over and over again, you end up causing memristors to start dropping their resistance in sort of a coordinated way. And you end up training the network to recognize certain patterns. And that's what they showed in this paper, is that you can take this simple array, present it, I think they might have used MNIST data, and they could then on a readout, and they showed in this paper, I think they built one of these, I think a small scale version of this, and then they scaled it up in simulation. So I think the test was actually in a high fidelity physics-based simulation, but they still were able to show in principle that you could present this thing with patterns and it would learn all by itself to produce outputs that could discriminate those patterns. So it's kind of a cool and kind of creepy thing. This weird passive array has neuroplasticity. It just naturally will recognize patterns that it's exposed to over time. And if you were to expose it to a different set of patterns, it would gradually erase its memory and start learning a different set of patterns. So its output kind of is a pattern recognizer for the most recently learned patterns. And it doesn't, it can do this passively, and it can remember, each one of these memristor states is stored for a very long amount of time. It's like this non-volatile storage where you could train it, and then deploy it somewhere. And you don't have to worry about those weights degrading over time, because if you just need it to recognize a few patterns, initially, once you start exploring it or exposing it to the rest of the world, it will start learning new patterns in the world. And some of those new patterns might be patterns it has never seen before. But at least initially, it will recognize whatever initial patterns that it learned in the lab before you deployed it. So it's this cool little architecture that does, spiking pattern recognition without any really fancy elements, just memristors at each one of these junctions. And this is just one of the approaches that people have been looking into and using hysteresis loops in electronic components to find even simpler implementations of spiking neural networks than the kind of more conventional spiking neural networks, which you see in these sophisticated architectures from IBM and Intel. All right, so that's kind of all right, let's see a question online. There's a question, is there a way to visually capture these patterns through a device and store them so that we can inject them back into this structure? Would there be a way to template these patterns or running different data sets to see if there was a commonality among these patterns? Everything about visually, if you look at the paper, you can actually see that they do have, a trace output here. So for each one of these outputs, they've got spikes. And so sometimes you get a spike and sometimes you don't. And these combinations of spikes and no spikes that happen on the output are the things that end up becoming a self-organized code for patterns seen on the input. So you can view them as, if your input is extremely high dimensional and your output's low dimensional, you can view them as clustering. You can view them as like an autoencoder, it's sort of dimensionality reduction or whatever you like. And so there's a lot of different ways that you can use these things. I don't know if there's value if you're asking about, what evolves in here, like the weights, how things are weighted inside here. I don't know if there's really anything that useful here because it is an over-parameterized system. There's so many weights inside here relative to the number of inputs. Then there's, I think, a bunch of different ways that you could get an input to output mapping that would manage to do the pattern recognition. So any one particular set of weights on the inside here isn't that special because there might be some other, just the way things were randomly presented might have generated another way to generate these weights. And so instead of being this line, this line might have been the one that was selected for the A letter instead. So I don't know if there's really a whole lot of value there, but definitely, take a look at the paper for more details. But it's pretty clear. This is an experiment you could do in the laboratory. You can watch spikes over time on the inputs and spikes on the time of outputs. You can capture these traces, and you can do, I guess, analysis of these traces if you want. But the big point here is that we have a way to do sort of dimensionality reduction in effectively a physical system. Just shows us that simple physical systems have the ability to do this type of computing. And all we needed was spikes and hysteresis loops. And there's tons of hysteresis loops in nature. And so it starts to expose the genius of spiking, is that maybe one of the reasons why we see spiking so much in natural systems is because we see hysteresis so much in physical systems, and maybe spikes and hysteresis, that's like the secret sauce. It's like an easy way to get neural network type logic going. And that's maybe what this is kind of exposing. It's another question online, or see, how does the difference between the resistance level affect the sensitivity of the structure to patterns? So the important thing here is that there are two resistances that are distinct. And so the important here with the memristor is that there are these two resistance levels that produce currents that we can discriminate in the tools that we have, and there can be these fan out effects, so that, I think you're going to probably need the accumulation of current downstream or something along those lines. I think people are just sort of figuring out how these systems will work. So I'm sure there are important tuning properties about how far away these resistances are. There's probably some theory about whether this resistance should be very high or whether there's sort of a sweet spot for this resistance and this resistance. And that kind of goes beyond my knowledge of this subject. That's an interesting question. And I encourage you to take a look at this paper to see if they've commented on that, because they go in pretty good depth on how they build each individual element, how they tested each individual element in the lab, and then how they went about expanding to a high dimensional simulation of these elements in a high fidelity simulator. So definitely encourage you to take a look at that paper. All right, any other questions about this basic idea of methods for neuromorphics? Okay. Well, as you can see, there are a lot of questions about, just training these things and understanding the training. And in one way, that seems to be a major gap between the artificial neural networks we've kind of come to talk about and these SNNs. And these SNNs almost seem like they're cool for associative learning, but if we really want to get down to all of the important kind of pattern recognition that artificial neural networks have become known for, feature extraction and all of the kind of the fitting processes that go on with ANNs, we need kind of a more efficient way to train them. And it turns out that, and I'm not going to go into great detail about this, but now there are several different approaches. Now there are several different approaches to extending backpropagation so gradient descent to spiking neural networks. So if you were to just go out and look through the literature about backpropagation, spiking neural networks, there probably are, if you were to trace that back, there probably are 3 or 4 different competing approaches that kind of came all out roughly at the same time, and then since then they've been elaborated on. So, again, I'm not going to go into detail on how these work, but I just do want to say that they do exist. And so now, if you have a spiking neural network, you don't have to come up with some crazy way to train it. There actually are ways to translate problems in such a way that you can train spiking neural networks in almost the same ease as you can train artificial neural networks, with the hope that what you get out will be a lower power neural network. So that's kind of the big thing here, is that backpropagation isn't for ANNs only. It can also be used for SNNs. Right, so SNNs naturally can implement STDP, but they also can implement backpropagation. So otherwise, there are STDP for SNNs to do associative learning, but the backpropagation is really good for supervised learning for SNNs. Okay, now I want to use that to pivot just a second here to sort of talk about how SNNs have started to make people think a little bit differently about ANNs, because there are some kind of clever things you can do with SNNs that people didn't realize that you could actually do with ANNs, but they had to use SNNs to kind of think through it. And one of those, and this actually comes out of a collaborator's mind lab, about putting neural networks to sleep to make them better learners. So what do we mean by that? And so ANNs suffer from catastrophic forgetting. So what do I mean by catastrophic forgetting? So in the context of continual learning, this is the case where an ANN learns task A, then task B. So imagine you've got task A, it's like recognize recognize all the cats in these images, in this image set. So find all the cats, classify all the cats. All right, great. You're really good at cat and no cat. So remember that, and now recognize all the dogs. So now we're going to train you to do dog and no dog. So we didn't do cat, dog, anything else. We did cat, and then we did dog. So cat, no cat, dog, and then no dog. That's one example of how you could do, one task and another task. Now, you might think that so then the question is, now after we've trained you, and by train you on task A, I mean we've gone through the train step, and then we did the validate step, and then we also then went and we did the test step, and they all worked out. So then in task B, we do the same thing. We do now train, we do validate, and we do test. And they all seem to work fine. And so we do this in a sequence. So we do A, then B. And it comes out of this sequence, and it's like 99% accurate on B. It knows dogs and no dogs, or whatever I said task B was. But then you go back and you retest on A. And very often what you get is catastrophic forgetting, which means that it forgets A. So even though it did so well recognizing cats and no cats, like that's either cat or not, now that it's learned that dog and no dog, it's like all those weights that got updated for it to understand what a cat was got overwritten or reused in some way to represent what a dog was. It's like there's finite space in there. And so the resources that it was using for cats, it didn't know that it needed to keep those sacred and don't touch those while it learned to do dog. And so when it was learning to do dog, it might have actually updated weights that were critical for it to understanding what cats were. And so artificial neural networks are really bad at this problem. They're good at training things. Like if you train everything all up at once, so you could say, here's a cat, here's a dog, here's a cat, here's a dog, interdigitate those together, then it will over time kind of partition things around. So it'll learn, that I need to learn the difference between cats and dogs, which means I need to maintain distinct representations inside the neural network for cat and dog. But if you train it on all cats and then all dogs, it's going to forget what a cat looks like. And that's just a common problem with continual learning in artificial neural networks. So there are a bunch of ways to try to deal with, to try to improve continual learning performance on artificial neural networks. And I could go into a lot of those different things, but so I'm not saying that what I'm about to propose is the only way you can do that, but there are ways you could say, well, if we know we're switching from one task to another, then we're going to sort of maintain like all the weights that were updated in task A, we're going to flag them as not to be updated in task B. And so that's one example. And there are a bunch of other things you could do too. Now, we know that people don't have this catastrophic forgetting problem, but we do know that when people don't sleep, they do have more problems with their performance on tasks they learned a long time ago. And just in general, if they learned a bunch of tasks the previous day, if they don't go to sleep, then they kind of get, just poor performance in testing those tasks, after. So sleep seems to be important for memory consolidation in humans and other animals, even insects. So, so I had these colleagues at a UCSD. So this is an example from Maxim Bazanov's lab at UCSD. And they used spiking neural networks trained with backpropagation. So they used one of the methods that you could do that. Now, what Maxime and his, I think, grad students and postdocs came up with is a way to implement neural network sleep that worked particularly well for spiking neural networks. And the basic idea is here, what do we mean by sleep? What you can do is you can connect SNN inputs to a noise source. So, I could say white noise. And it turns out the different types of noise that you choose here do affect the performance of this. But in general, it's kind of important that it's just uncorrelated noise. So all the inputs are just getting noise. So spikes. So just random spikes at random times. And while that's happening, what's interesting is the neural network starts to sort of replay what it's learned that day. So because certain weights inside the neural network have been reinforced, then as you get a random spiking of this white noise coming on the inputs, if you look to see which neurons are firing, you actually see firing patterns that you saw during training. And that should kind of make sense because during training, those weights got kind of reinforced, so now they're easier to fire. So if you just sort of randomly fire all of the inputs, then the ones that have already been trained are going to be more likely to kind of spontaneously fire. So what he said is that during sleep, you then turn on unsupervised learning. And think it's kind of like Hebbian learning, although they do anti-Hebbian learning. But those details don't really matter too much here. And what that ends up doing is it causes weights that fire a little bit, but not that much, to be kind of driven to zero. And it causes weights that are very sensitive to be driven even stronger. And this manages to create sort of a partitioning in the weight space between these tasks. So what he does then, so this is what we're going to call the sleep phase here, those two together. So what he'll do is he'll train on A and then do sleep and then train on B and then you can have it do sleep. And then test on A or B. And it turns out you get good performance on both. But if you get rid of the sleep stages, then you only know B. So the sleep actually creates a partitioning among the weights where this sleep makes these A weights really strong, and it creates a bunch, and all the weak A weights that don't really correspond to A, they end up kind of going to zero. And those end up being the ones that the gradient descent end up having the strongest effect with B. And so those end up being the ones that are mainly learned for B. And then you do sleep, and it does further consolidation. And so when you actually look at the representational space of what weights were learned, you end up getting like a set of weights for the A task that are distinct from the set of weights for the B task. So sleep reorganizes the weight space in a way that simple gradient descent can't do, because gradient descent doesn't know about all these tasks simultaneously. So this is an example where it's an argument that neural networks themselves might need to be put to sleep in order to be able to provide this continual learning. Now, this was really easy to implement in spiking neural networks, but now that they've done it here, they realize that there are analogs here. Like we can actually come up with ways to sort of tie noise sources to standard artificial neural networks. And we definitely know we don't need, so this case, this is like spike timing dependent plasticity, but we know we have Hebbian learning rules for normal ANNs that just do these weight updates, these arithmetic weight updates. So it turns out that this can also be implemented with a normal artificial neural network. So this is inspired by thinking about spiking neural networks in the way the brain uses sleep, but it's now inspired ways to think about enhancing normal artificial neural networks so those ANNs can continue to do continual learning. So it's just one example of how even if the main contribution may not be to spiking neural networks, probably wouldn't have thought about, well, maybe would have gotten there, but it was a much more direct jump to think like, what's going on in a brain during sleep that allows brains to do continual learning? Well, the brain is so different than the neural network inside a standard computer that it's hard to make those analogies. But if we have something that looks a lot more like the mechanisms that are going on in the brain, it's a lot easier to make those analogies, to test out these ideas. And when they work so darn well, and they're even working with backpropagation being involved in the training, it then finally gives us a pathway for us to import it to ANNs, which seemed like that ANNs just seem so different than normal, the neural networks going on in the wetware in your head. Okay, so that's kind of the message here. Is like, I'm not saying sleep is going to transform all of neural networks, but the general message I have here is that we probably have a lot more to learn about real neural networks that'll make us introduce mechanisms that we haven't even thought of before. And if I had more time, I might sort of muse about neuromodulation, which I only mention briefly here. And neuromodulation is something that goes on in your head all the time. And basically, it allows one neural network to be used in multiple ways. So one neural network used in multiple ways. And basically, you can imagine if I've got a bunch of synapses that have been trained in my brain, under different contexts, my brain can actually flood itself with neuromodulating chemicals, which change the way the sensitivity of those weights. So I can train my weights, so those weights are fixed, but it adds kind of a little bit of bias or a little bit of challenge to each one of them. So it allows you to learn multiple things with the same neural network. And so neuromodulation has also been proposed as a way to deal with continual learning and artificial neural networks, but we don't really have the frameworks to implement neuromodulation right now. So this really involves us thinking about all of the chemical multi-modalities of real neural networks. So in other words, you train the sensitivity of these, these junctions, these synapses between axons and dendrites. When you learn something, we're taught that it's enhancing the receptors or it's enhancing the amount of neurotransmitter that's being put into the synaptic cleft. And that's true. But even after you've trained those neurons to be more or less sensitive to a particular neurotransmitter, you can then in short time periods modulate that. You can take a drug and it makes you more excited or less excited, as people do when they need to, maybe treat themselves for bipolarism and things like that. And your brain is constantly manufacturing pharmaceuticals that over short time spans, it can use to make you more alert, less alert, more sleepy, less sleepy, et cetera, and can actually make the circuits that have learned one thing actually end up performing at a different thing. So you can learn multiple tasks in the same circuit just by modulating those, by changing sort of large scale properties of networks. And so you can kind of tell this network you're in context A or you're in context B. So the synaptic weights don't change, but the kind of global scale sensitivity of that region changes, and it allows for kind of a it allows for multiple modules to be implemented with the same wetware. And so these sorts of things are things that we know very little about, and we aren't quite sure how to import them into our artificial neural networks, but we do know that they're super important in what's going on up here. And if we want something that's in a machine like that one over there to start acting like a machine like this one here, then I think we really need to take seriously not only things like sleep, but also things like neuromodulation and really getting closer to the true chemical dynamics of what's going on between neurons. Anyways, well, that's the last thing I want to tell you about neural networks. On Thursday, we'll start our new unit on interacting particle systems and cellular automata. But I don't want to keep you any longer. I appreciate your patience this morning. If you have any questions, please feel free to come up after or questions online. And otherwise, I'll see you Thursday. All right, I see a question online about sleep. From the ANN perspective, it doesn't necessarily know task A and task B are two separate cases, so it will overwrite. That's true. Are there methods that bake some type of task ID? Yes, there are task labeling methods in the continual learning literature that you can say, right now we're learning task A, and then you can say, right now we're learning task B. And when that happens, then it can tell the neural network effectively to incorporate that into its encoding. So, that's, and then during sleep are outputs measured? They're not, I mean, they're measured scientifically, but they're not measured in practice during sleep. So they're measured to sort of know what's going on in sleep, but they aren't useful in any way that I know of. The question about what is sleep accomplishing? Is it just accomplishing some randomization of weights and spikes involved? Is there a more efficient way to induce randomness than a bunch of noisy inputs? There are replay mechanisms that do something similar to what sleep. So what a lot of people do is they actually store a buffer. They actually add memory to neural networks that store a bunch of the training tasks from the previous bout of training. And then when they go into a sort of a sleep phase, they actually replay those training data. So if you learn task B, after you learn task B, you actually get played back the A that you had already learned earlier. And then hopefully the back and forth interleaving that they force will force things to separate out in weight space. And so that's one way to do it, but it requires keeping a lot of memory because you have to retrain yourself on all the same training data that you did before. What the sleep is trying to do is to do that without having to store this replay buffer. And so what they find is by randomly tweaking all of the inputs simultaneously, then you end up getting firing patterns that happen in the brain that look as if you're relearning A again. So after you learn A, under random inputs, you're more likely to replay A. And after you learn B, after random inputs, you're more likely to replay B. And so the idea here is that by forcing your brain to replay these things, because the unsupervised learning is turning on, it will actually reinforce that as if you'd turned on supervised learning on A again. So you can either replay real A training data that you've already learned before and turn on supervised learning, or you can turn on unsupervised learning with random noise and you get a lot of the same output where effectively the training data for A is stored within the weights. You just got to force the brain to recall those weights and strengthen them. So it's strengthening those weights so that it's harder for them to be overwritten when you learn B. So I don't know if that helps.
Yeah, that helped a lot. Is my mic working?
Yes, I can hear you.
Okay. So as for the first question about the task labeling thing for continual learning, how does that fare when compared to the sleep idea?
Well, so I'll walk in front of the camera. So the idea behind task labeling is that, I mean, that should work. Task labeling makes the problem really easy because you have this extra input that you know that I've moved from one task to another. So as long as I have kind of enough memory, then in theory with task labeling, you should be able to reach an architecture that has zero forgetting because you kind of know that, well, oh, you're right now I'm doing A again. So you can kind of, if you have enough memory resources, and by memory resources, I mean like, if your neural network's big enough, then you should be able to partition off like these are the A weights, these are the B weights.
Sure, yeah. Well, then you
weights.
just have like two separate networks or a million separate
Exactly.
networks. Is there any way, have they done like some kind of hyper network idea where you have one network, but you're kind of generating the weights on the fly? Maybe the tasks are interconnected, like the sim sets, or I can't remember, but it's like AlexNet would have different categories of recognition, and they're kind of like vectorized. They're related to each other, so it could tell even if it hasn't seen this number before that, like, okay, well, it's in the tree area. It's right. So maybe it could generate. I don't know. Has anything been done like that?
Yeah. In fact, there's a relatively recent paper. I think it's out of Google Brain on task agnostic continual learning. If you were to Google Scholar for task agnostic continual learning, I think you'd find this recent paper again. I think it's out of Google Brain, and they implement what they refer to as kind of a what network and a how network. And their basic idea is that they look at the current tasks coming in. So this is an idea that if you didn't have labels, then it's this kind of idea that you need to figure out what task you're doing first, and then once you have that task, then you sort of figure out how to do that task. And like you just said earlier, if you had like, you know, infinite resources, you could just, once you know the what, like which task, you just, you know, you dial up that neural network. But you know, it's going to be really inefficient to have a whole deep neural network just for one task, and then a whole new deep neural network for another task. So what this what and how stuff is they've come up with kind of an interesting latent variable kind of, they kind of decomposed the latent variable space in a way that the what is actually not like a task ID, but it's actually a complex vector encoding. And the how itself is also this kind of complex encoding. And those two merge together to produce the weights that actually are the input-output mapping for the real task. And so this is a way to somehow partition a single neural network where you're sort of, it's almost like coding theory, where, or it's like code division multiple access on cell phones. Like, you know, like in order for me to use the same airwaves as you, I have a special code that corresponds to me, and all of my data gets obfuscated with that code and gets sent out, and it gets obfuscated with your code, and they all add to the same physical airwaves. But when it needs to come back to me, I can actually multiply the airwaves by my code and only get my data out, and you can multiply the airwaves by your code and only get your data out. It's kind of a similar way to share the neural network resources. So that, I mean, it's kind of a little hand wavy, but it is that same idea that you can kind of partition these in a sophisticated way, but you need kind of a sophisticated how as well as a what, as opposed to just a simple like, you know, this is ID 1 and this is ID 2 and so on.
Yeah, that's exactly the type of thing I was thinking of. That's great. I'll look into the task agnostic thing.
Continual learning. Yep.
Yeah.
Great.
Definitely. Thank you very much.
No problem. Any other questions online? All right. In that case, see everybody Thursday for the next unit.